Professor Peter Wonka from Saudi Arabia. And so his talk is about semantic image editing using Gans. So just a very quick overview of what Peter has done. Peter is currently a full professor in the computer science department at Cost, and also the interim director of the Visual Computing Center. And he's done lots of interesting work in the areas of computer vision, computer graphics, remote sensing, image processing, visualization, and machine learning. His recent interests mainly focus on deep learning, generative models, and 3D shape analysis and reconstruction. Okay, so I think, we also have the second speaker, who is Taigui Zheng from Xi'an University. I think I'll introduce the second speaker a bit later, so that I'll hand over to Peter for his talk on semantic image editing using Gans.
All right, thank you. Can you see my screen now, or do I need to reshare?
Yeah.
You can see the screen?
Yes.
All right. So I'm going to talk about image editing using generative adversarial networks. In the last years, there are many competitors in the area of generative models. Generative adversarial networks have been one of the best models for many years now, but very recently we saw strong competition from two other models. For example, the two models are various types of diffusion models and various types of autoregressive models using transformer. A bit behind in quality, I would say, are flow models and variational autoencoder that are not really competitive, I would say, at the moment with these three other models. However, it is also important to consider that many current models use a mixture of different types of concepts. So you could see models that use a variational autoencoder inspired compression into a discrete latent space, also using a Gans loss, and then in a compressed latent space, you would have an autoregressive model using a transformer. So that means the distinction is no longer that clear because of this mix and match architecture building that's going on at the moment. But this talk, I'll mainly focus on generative adversarial networks. But just so you have some idea what others are doing, here's the DALL-E 2. Now, I cannot verify this. These are just things people posted, and one of my students found them. So I cannot really say if these were truly generated by DALL-E 2, but you see, for example, on the right, a dramatic depiction of Elon Musk buying Twitter, and DALL-E 2 can, from some text, give you an image. And this is more like a painting style image of a human, but on the left, you see maybe the type of human that DALL-E 2 can generate. And DALL-E 2 is, I would just take as representative of a very strong diffusion model at the moment. For generative adversarial networks, if we go in there, then right now the big distinction would probably be between 2D Gans and 3D Gans. And this talk mainly focuses on 2D Gans, even though if you followed the literature, you saw a lot of papers coming out within the last half a year that tried to generate first a volumetric nerve style representation that is then being rendered And so the idea is that the GAN would generate a 3D representation itself. There are many choices, and I just list some of them. I think this is not exhaustive of what was done within the last half a year or so. Gram, StyleNer, StyleSDF, Volume GAN, SIPS 3D, and EG3D. And I highlight EG3D because I would pick it as the currently best model. So here are some results from EG3D. You can see that the generated faces are just a bit less in quality than the faces generated from a 2D GAN. However, in addition, you do have a 3D representation in the back that gives you maybe a better understanding, a better semantic interpretation of the space. Now, this will be work going on now, and you already see editing papers, of course, coming out with 3D GANs. But for now, we stick with 2D GANs for this talk, which is the work that was done primarily within the last 2 or so years. And I'll also focus on work done in my group. For 2D GANs, there are many options of what to pick. And I would say that almost without competition, people work with the StyleGAN generator and versions of the StyleGAN generator. So the competing GAN architectures are simply different versions of the StyleGAN architecture, not so much different types of architectures. The StyleGAN architecture has 3 or 4 main versions: 1, 2, StyleGAN 2, Ada, and StyleGAN 3. But the question is if StyleGAN 3 is really better than StyleGAN 2. It has a lot of interesting features that can be useful, but I would say for now, the agreement is still that StyleGAN 2 Ada is the best 2D generator, specifically for faces, and faces are the first and dominant application when it comes to generative adversarial networks. And still, there's a choice of which implementation to use. So there's TensorFlow versus PyTorch, or original versus some re-implementation. So there are going to be a lot of details to consider there. However, many people would now pick StyleGAN 2 or StyleGAN 2 Ada. And so most of the editing results that were published, they are built on StyleGAN 2 or StyleGAN 2 Ada. All right, so let's look at some GAN images. This is one example of a GAN-generated image that can be achieved by StyleGAN 2. This is another example. And you can see that there's this blurred background mimicking some portrait photography. And then the foreground has a really nice face with all sorts of details. And the image to an untrained observer or layperson looks more or less indistinguishable from a photograph. So as comparison, these are virtual humans. These are 3D models generated and rendered. These also look pretty good now, but probably still a bit too clean, and they don't have some of these noise features or variations that are present in GAN-generated images. Let's look at the GAN architecture. And while GANs, they need a generator and a discriminator, I will not mention anything about the training of the GAN. You know, how does the GAN learn, or how does the discriminator look like? I will only talk about the generator, because the generator is what people use for editing. So this is a very old generator, I think from 2015, from Rashford, but I'll just use it to illustrate the concept. What you see is basically an input way to the left. These are 100 random values. And as output, you get a 64 times 64 times 3 way on the right RGB image. So that was 2015. And what happened to get from this 100-dimensional vector to this image is that the architecture had a lot of convolutions and upsampling operations. And so this is pretty much still the concept that's dominant today. So in some sense, this part, the generator, it looks like an inverse classification network, or if you're hopefully familiar with all the dense regression tasks, such as segmentation or depth estimation, that are built on this unit encoder-decoder architecture, the generator is very similar to a decoder. And one other part of the architecture is what is called a mapping network. And in this mapping network, you start, and this is now the StyleGAN version, you start with a random vector set that has 512 components. And all these FC are fully connected layers. So this is a multi-layer perceptron with 8 layers that takes one input vector Z and maps it to one output vector W. So the difference here is that the input to the mapping network is the vector Z, where each of the 512 components are sampled randomly. So there's no relationship between two components, and no component really knows what the other one is doing. They're really generated completely independently. But after going through this fairly deep mapping network, we have a W code where the variables have some knowledge about each other. So the idea of such a mapping network is that the W code really tells you all the information you need to know about a single phase. And now we're gonna basically go back and modify this basic convolutional generator so that it not only works with a random vector as input, but it works with a W vector that can control how the generator functions. So now what we see again to the right, and this is now the more appropriate StyleGAN generator, that not only goes to 64 squared images, but it outputs a resolution of 1024 squared. And again, this is RGB. And what the choices that the choices are for this architecture design is, what information do you basically insert way at the beginning that was this maybe set vector way in the beginning, and what information do you insert at each convolutional layer? So this is this green information here. So the choice that StyleGAN made was to have basically nothing that is input in the beginning, just a constant, and mainly rely on this information injected from the side that is based on the W code. So let's look at how can you actually realize this? How can you insert global information or noise into one particular layer? So there's multiple ways to do this, and we'll just look at one option here, that is option C. And what you see is there are these green blocks called conv blocks. These are regular convolutions. And as you know, a convolutional layer takes a tensor as input and gives you a tensor as output. So let's just imagine we have a 64 times 64 times 512 tensor as input, and a 64 times 64 times 512 tensor as output. And then how that means we have 512 what we call activation maps of size 64 squared. And how do each of these activation maps look like in the style Gan architecture? Again, we stay with faces. They look something like this. So each of them looks somewhat similar to a face, but something highlighted. So you could interpret something in there. So if you look at the example to the right, looks like it has something to do with the eyes or the area under the eyes. And if you look at the example to the left, looks like it's something to do with a highlight on the head or maybe with the hairs. So either way, these convolutional layers, they process these tensors with lots of these activation maps. And then the way to inject information, this is from this A block in here, is by modulating an activation map, which means simply we take one activation map like this, and we multiply it with a global scalar. So we make the whole map brighter or darker, basically. So this is how everything is put together now. Again, this is the old architecture. So this is then how exactly this is injected is slightly different now. But overall, still you have the mapping network that you see on the left, where first you have this latent set that you process with this MLP to get this global vector W. And this global vector W is then injected into every layer or every convolution before or after. And this is how the thing is controlled. Now, there's also a noise, and the noise is injected differently. The noise is really injected per pixel, more or less. I mean, there are some details, but the noise is really just something to add spatial noise into all these activation maps. All right, so image generation itself is then often just written as a function G that takes an input W code and generates a 1024 squared RGB image. So you see image equals generation of W. So there's some question of how does the GAN exactly generate the images? So top down, maybe you imagine it generates something like some segmentation masks and then adds more details. Or maybe it says here the eyes and then adds some details for the eyes. Or maybe it generates some 3D model and renders it somehow. That doesn't happen automatically unless you use a 3D GAN. Or maybe it has some sort of basis functions that that then are combined, similar to maybe the eigenfaces concept. And the answer is that the GAN does not really generate the images in an easily human understandable manner. So if you look at all the intermediate information that the GAN processes, it is actually not that simple to come up with editing operations that work really, really well. However, you can get editing operations that work still quite a lot better than people expected just a few years ago. All right, so this would be some example person. And again, now, if you look at this person and the maps that we saw before, okay, so maybe you thought, okay, these high values here around 4, maybe these are some highlights, but then again, here you basically don't really see highlights. Or, what does that correspond to? It doesn't, maybe the eyelids below, but it's kind of hard to see. And then why is this eye information packed together with something that goes over the shoulder down here? So it's a bit tricky. Or you see maps like this. And what is this right one? You have something about the front teeth and something about the eye. So it's not that clear. All right. So what operations can be performed? One fundamental operation is taking an RGB image and converting it back to a W code. So we want to have some operation that can do what I call embedding here. There are two ways to do this. One is optimization-based, and one is encoder-based. That is, you train a network architecture that takes an image as input and then outputs a W code. So the embedding is a bit tricky because everything looks great if you look at it from distance far enough, but things can start to look a bit weird when you really zoom in. So for example, if you look at the images in the top row, so the left is the input, and then you see the embeddings, different types of embeddings. They look very similar on some level, but maybe if you zoom into the eyes, you see that the eyes look more realistic early on, maybe in the third column, but then in the end, the eyes, they kind of lost their shininess and they no longer look very natural. See the same issue in the bottom. So this embedding generally is a trade-off between how can you optimize the pixel-wise loss, so how close can you really get to the input image, and how semantically meaningful is it. So while the L2 error, pixel-wise error, might be lower, in the end, here the overall quality is not that high. So here's a comparison of different algorithms. And for a lot of them, especially when you look at them right now, you will see that this is actually not that easy. If you look at it just for a very short time, then everything looks kind of okay, a little off, sometimes it's a lot more off. And so actually the analysis of the different embedding algorithms is a difficult problem by itself. And especially because there's this trade-off between semantic editing quality and how similar does it look like to the input. So people, including us, studied different embedding spaces, and the W space is the most natural one, but very early on, and this is also what we did, is people figured out that the W space itself is not powerful enough, but you need to embed to some other spaces. So you actually have more possible faces that you can encode. So this is very early work, image to style GAN, that we worked on. And then what you see way on the left, if you go to this more extended space that we call W+, you can embed faces such as Obama, but you can also embed a cat and a dog and a painting and a car. And then the obvious conclusion is that, of course, you can embed faces nicely now, but the fact that you can embed other things should be not a great success, but more like a worry, because the embedding cannot really be semantically meaningful. Again, trained on faces is not able to then manipulate the car. I mean, that seems impossible. So that means the space is kind of too expressive now, and it's also possible to just overfit and embed some nonsense. So this is what people looked at: noise, which is the part on the right, the Z, which is what goes into the mapping network in the beginning, W, which is the default output of the mapping network, and W plus is simply if you go from the output of the mapping network, you see all these arrows going into these A boxes. And per default, the W code is simply replicated 18 times or something like 18 times here. And it's possible to split it into 18 different codes instead of having the same W code for each time the W code is injected. So that's what's called W plus. And then this W code goes through a fine layer. This is this A box here before it is used to modulate. And if it not use the W code before it goes into the fine layer, but we use the codes that come out after this affine layer, these are more or less the scaling factors of the individual activation maps. This is called the style space. Now, another thing would be to kind of split the network somewhere in the middle. So let's say there's some upper part that you would see here in the lower part. You could cut the network and look at the output of one conv layer somewhere in the network, or maybe some modulation layer. And so this would be a tensor. Let's say it's a 64 times 64 times 512 tensor. And you can say, okay, let's ignore everything in the generator before. You can cut the generator in half, ignore the first part of the generator, and directly embed into these activation maps. And the other way to do embedding is to embed into the generator weights themselves. So this would be the weights that the network has to control the conv layers. All right, so the straightforward interpolation of images is one editing operation that you can do now. So now it depends on what exact embedding you use. So for this, we assume you kind of use the W code embedding. Could be W plus, or could be style space, could also be tensors. And so what you can do is then a simple linear interpolation of the W codes can give you an interpolation of images. And to make this one very explicit, you would have two RGB images. You would start by embedding the first image to get the first W code. Then you embed the second image to get the second W code. Then you do a linear interpolation. And then you use the generator G again to generate an RGB image from this interpolated W code. So these are some early results. And this is some more fancy interpolation in style space. This is a paper style fusion from Danny's group. And what they try to do is not to do a simple interpolation, but basically use an MLP network to do a more fancy interpolation. So one example that you see here is the idea of hairstyle transfer. So what you want is you want to interpolate the person way on the bottom left with each of the people on the top row. But in particular, you don't want just some arbitrary interpolation. You would like to have some interpolation where the face mainly is kept from the person in the bottom left input, and the hair is taken from the person on the top. And so what this tries to do is to find some interpolation of two latent codes where, one is mainly responsible for the hair and the other one for the face. And then you can see that this works reasonably well. Not like super well, but it works reasonably well. And so these more intelligent interpolations or latent code combinations are possible. Now, semantic editing, there's the idea to learn just vectors in latent space. We'll just stick with W for now. So for example, WH, pose, smile, lighting, and then you can edit an image by adding vectors. So you start with the W code W, and then you add plus theta, where theta is the edit strength, another vector W smile. And this vector W smile is global, that is used for all possible images you want to edit. It's kind of a constant that you learn in a pre-process. And then you have the edited image WX. So this is some version we worked on that not only uses a linear edit, but it uses a nonlinear edit using normalizing flows. And you can see here, this is an edit for doing a pose change. And then if you look at 3D Gans, what people worked on now, this pose change somewhat looks like plausible 3D, but it is not really consistent. So it's just like some illusion that's approximately 3D, but it is not really a consistent 3D rotation or dew point change. So now, instead of just doing embedding, you can actually do a lot of editing operations with something like conditional embedding. So for example, you see some 3 faces here, but here we only want to embed the left part of the face, and the right part we want to keep free, and we want the network to pick whatever it thinks is plausible. And so here we can use, again, the semantic information stored in the GAN. And to do that, you simply modify the loss a bit to have some sort of a masked loss, or there's a loss that compares images after some transformation. And so you can get results like this, where you see the outputs of different algorithms. And in general, even though there are differences, all of the GAN-based methods can do a good job of inventing a plausible second half of the face. And this is hard to do for other non-GAN-based in-painting algorithms. So this example is super resolution. Again, it's just some slight modification of the embedding loss, where what you see in the second column is some input, the downsampled image, and then you want to generate a higher resolution image. In contrast to traditional super resolution, here you go really several steps of increasing by a power of 2, and not just make the resolution 2 or 4 times larger. This is colorization. So again, the second column here is the input, is a grayscale image, and then the GAN is able to give you a colorized output. Now, one question that, so a lot of this work here is based by embedding, conditional embedding, or manipulating the codes. So the question is, can we also just do copy-paste image editing in using Gans? So what you see here is an input person on the left. There is a man, young man, and then there is a woman to the right. And so what we want to do is we want to copy the hair from the man to the woman. And so this is a terrible result if you just go and copy the pixels directly. But in some sense, so what we want to do is we want to maybe do this pixel copying, but we want to do it in earlier, using the GANs, but using earlier layers. So if you see a generator network here, then maybe we can do some partial embedding. So we, or activation map embedding, we embed into this part of the GAN where the resolution is 64 times 64. So we can do we can take 2 images, we can embed them and make them both 64 times 64 tensors in the embedded into the GAN, and then we do pixel copying at this part, and then we use the generator to generate back the 1024 image. And the idea is that the generator will do an intelligent combination of the pixel copying that kind of created some ugly boundaries, and we hope that the other layers of the generator go back and fix it. And so we did this very early on with ProGAN in the paper TileGAN. And what you see is on the way on the left is some mountain that has, or is some aerial image that we have 4 different tiles that we copy together, and you see very hard boundaries. You can slightly make it a bit nicer using GraphCut, but if you actually use the GAN and use the editing operations, pixel copying in earlier layers of the GAN, and then use the generator to fix the boundaries, you get very nice semantic blending between the regions. And so basically, there's an issue though with StyleGAN because of the W code that you need to control the later layers. So there was no global control in ProGAN, but in StyleGAN there is. So should we then use the W code from image 1 or image 2? There are all sorts of these occlusion problems that possibly require in-painting, and you kind of have to be careful to adjust the lighting and the colors. And so this is one thing we worked on in Barbershop, but the basic idea is what I just explained. You want to embed into somewhat halfway in the GAN, do the pixel copying operation there, and then use the generator to generate the final result. So here are some results, and what you see is a segmentation mask, and I'll skip it, but you just see the two inputs in column 2 and column 3, and then there are the results of 3 competing methods, with the last one is the result of our match. So one last thing is how to use GANs for domain adaption. So you have one original generator in domain A. Let's just say again, that generates regular faces, such as this person on the bottom left. And what we want to do is we want to fine-tune the generator so that it outputs similar faces, but in a different domain. For example, this cartoon domain, what you see on the bottom right. And one notable paper in August last year was the Style Ganada, also from Dennis Group, where they just used purely text-based supervision. So you could say that, okay, we have a dog generator that created realistic dogs before, but we give a text prompt that says, the dog should look more like the Joker. And then there are going to be some losses. So this generator B should be fine-tuned such that the output is still similar. So there should be a relationship between whatever the domain A generator outputs and whatever the domain B generator outputs, but the domain, the style should be taken from the text prompt, and this is done with some loss in clip space. And so we built on that for building more classical single-shot domain transfer. And the interesting part is you can do a reasonable job fine-tuning a generator using just a single image. So what you see on top are the realistic input images that we're going to embed. And then on the first column, you see all the style reference images. And then the results are shown row by row. And you can see that really the fine-tuning is able to learn a different domain from a single input image. All right, we did some work for segmentation. Skip. All right, also skip. All right, let's just skip to the end. So thanks for your attention, and maybe I can take some questions.
Yeah, thanks, Peter, very much for giving this nice talk. You obviously give lots of potential applications by manipulating, GAN space. Any quick questions from the audience? Yeah, so I have a quick question. So you mentioned about this adaptive foundation, which you can sort of potentially manipulate different parts of the images to control the generation. That seems to imply that these aspects need to be disentangled. So is there any way how this is guaranteed, and how if there are if this disentanglement is not perfect, is there any direction that can potentially be improved?
Yeah. So exactly. So in some sense, what people want to do is they would like to have an entangled representation, but I think there's a fundamental conflict, that is the GAN needs to learn the relationship between different regions somehow. For example, the left earring looks more often than not the same as the right earring. No, it's not guaranteed, but more often than not, they are the same. And so the GAN needs to learn that. Or the left eye looks similar to the right eye, and the hair everywhere is the same. And also the lighting you can see that the GAN does a great job generating consistent lighting. So the lighting needs to be the same everywhere. And in some sense, the GAN could not possibly, in my view, create the perfect disentanglement that people think is necessary for editing. Because in editing, you want to say, change the right eye to brown, don't care about the left eye, or just change the hair. But you need to make the lighting consistent somehow. And so there's a lot of work and claims about disentanglement, but in some sense, I think there is no real fundamental insight except for the GAN is a bit disentangled, but not as much as you would like, and there's no solution to it. And it's unclear if the solution is even possible or how far
sure.
you can push it.
Yeah. I mean, clearly there are conflicts between a perfect generation and entire disentanglement. That there will never be there will never be a perfect solution to address both sides. I mean, I think from a human observer perspective, they may have some sort of judgment to see, okay, this is a good balance. How we can sort of learn a model that knows how to achieve this kind of balance can still be interesting, even if there's no perfect way to change certain attributes, but also ensure the quality of the final generation.
Yeah, I think in some sense it's it's a fundamental question, but my feeling is people more or less gave up on it because they say it's as entangled as it is. We try to do the best we can to get the application we would like to work.
That's kind of something way to show that it's good enough for certain applications. Talking about applications, I think you showed examples where lots of applications can be done by embedding in the GAN space a certain input image. Now, you can achieve something like massive super resolution, but there's always been a potential risk. So one example you show is like a very low resolution input, but the ground truth essentially that the person has mouth closed, but the generation actually has mouth open in a few slides back. So can you still find the slides, by the way?
Can we go back?
Yeah, it's just a super resolution example.
Yeah. Okay. Yeah.
Yes, that's right. I think, the last example. So I think the input is so low resolution, it's pretty hard to tell whether the mouth is open or closed. And clearly, obviously, the reconstruction looks convincing, but obviously, still a bit different from the ground truth.
Yeah. So the ground truth is mainly shown as some other comparable quality interpretation of the lower resolution model. And then
it's not the real ground truth then.
Well, no, I mean, it is the ground truth, but there are many possible interpretations for the low resolution.
Yeah.
So we just know that this is one possible interpretation that is valid. And the ground truth will have a better fit to the low resolution, of course. But in some sense, it should be possible to find other valid images that correspond to this low resolution model, not only the ground truth is more where we got it from.
Yeah, sure. I mean, given the loss of information, it's you'll pose problem. So certainly there won't be a unique answer that tick all the boxes, and that's correct reconstruction of the input.
Yeah.
Yeah. But I guess for other cases where you do the GAN embedding, there's always a kind of subtle changes, as you mentioned in the previous slides.
Yes. So the GAN is mainly good if you give it some freedom to cheat a bit. It is not good for very precise operations. So even for you have this let's say colorization. The image gets colorized, but it's not no longer exactly the same as the input. So for example, the woman on the top row, it had an earring in the grayscale, a nose ring in the grayscale that all the GAN colorizations ignore and then remove. So it's in some sense, the GAN needs this freedom to cheat a bit to get the quality it gets.
Yeah, I mean, I guess that's a rare feature in any training data in this particular case. So given this this flexibility, would that be possible for the scan algorithm to generate multiple outputs for the same input, which are all plausible, or they tend to just generate one result they believe to be the best?
Yes, so that's definitely possible, but as far as I know, people have not had no one had great success to do it. So you can see some examples in papers, not only ours, but these examples are always worse than you would like them to be. And I think part of the problem is that the optimization algorithm itself biases the results. For example, many people initialize with the center of the latent space, and then you just don't get the variations you want. And even if you then use different initializations, then maybe the quality goes down. So it's possible, but overall, people have not been super successful in getting many different variations.
Thanks very much. Any questions? Any more questions from the audience? Any chance for the last minute question? Okay, if you don't have more questions, let's thank Peter again for the really nice talk. I think lots of really interesting insights into this problem. Yeah, thank you.
All right, thank you.
I think I probably should have shared my screen. I think I kind of missed out how to do it probably last time around. Yeah, so just a quick overview of this each webinar session 9. The second talk will be given by Professor Taegui Zhang from Xi'an University. So this is a quick overview of the speaker. So Taegui Zhang is a professor at Xi'an University. And before that, he was a research scientist, a postdoc at BCC of KOST and ICSI, UC Berkeley Max Planck Institute for Informatics. He obtained his PhD from KOST under the supervision of Professor Helmut Poltmann and Professor Peter Bonker. He has done lots of interesting work in the areas of geometry modeling, geometry processing, architectural geometry, graphics, and computer vision. Okay, Taegui, I think the time to hand over to you.
You're muted. All right.
Oh, sorry. Can you hear me?
Yes.
Okay. Thank you very much for your nice introduction. Today, I'm very glad to present my work. I call it Geometric Modeling from Flat Sheet Material. So this topic is a summary of my research in the past few years. So here is the outline of my presentation. I will first introduce the background and follow with 3 specific research within this topic. The curve pleated structure, freeform quad-based Carigami, and shape morphing mechanical metamaterials. So these are the 3 basic concepts you may know: origami, Carigami, and developable surfaces.
Hi, so can I interrupt you? I think we only see a background image rather than the slides.
Sorry?
Can
So
you
we
share
can
the
only see
screen?
like
I think
yeah.
it's on my screen share.
Okay. So yeah, I can't see your screen, by the way. Can you please share your screen?
Is it fine now? I need. So can you see the screen? I don't know what's the problem.
Okay, sorry. I think that's the problem. I still need to switch to your screen. Okay, that's fine. No problem.
It's fine. Okay.
Yeah, it's fine. Yeah.
Okay, let's continue. So these are three basic concepts you may know: origami, carigami, and developer surfaces. They have a common feature is that they can all be modeled from flat sheet material. So first, let's look at the origami. So origami is a Japanese word, means paper folding. It's kind of very old art. I think almost everybody has more or less some experience of playing paper. So here I show some examples of origami. So here are two boats, a swan and a frog. Someone could make even more complex designs such shown here. So origami has a very old history. Here is the first known book about origami, which published more than 200 years ago. But the concept and the designing idea has been widely applied in the modern technology, such as the designing of solar panels for space exploration. Here you can find NASA's design for International Space Station on the upper left and Mars rover on the upper right, and two other designs for the solar panels of a satellite below. So other than that, origami has also been used in the field of soft robotics. Here is an example from Harvard University where origami is used to simulate muscle motions. The carigami is another concept. Still, a Japanese word means paper cutting. So compared with origami, the difference is besides folding, cutting is allowed in the design of carigami. This means carigami has more design of freedom for geometric modeling. So the idea of carigami has also been widely applied in the field of material science and also used in the art design. So on the right is a pop-up structure. So here are two more examples of carigami. After cutting a planar sheet material, the left structure shows new material properties and also rich variation of curvature. And the right one shows an orthotic structure expanded from a square to a circle. So the set concept is a developer surface. Developer surface is a smooth surface with zero Gaussian curvature. It can be flattened onto a plane without any distortion, stretching, compression, or cutting. So smooth developer surface can be divided into three categories: general cylinder, general cones, and the tangent surface of a space curve. So flat sheet material are the most common form of raw material. Then developer surface is widely used in the manufacturing-related modeling. So it can be used in the field of architecture design and also in the manufacturing of boats, clothes, shoes, and others. So origami, carigami, and the developer surfaces are the main focus of my talk. So next, I will introduce curved pleated structure. So I consider it as an origami related and also a developer surface related work. So our work was motivated by discrete differential geometry and inspired by curve folding art, such as shown here by Eric Daman and his father, Martin Daman. Here, the curve pleated structure is kind of origami with zigzag curve folds. So in the traditional origami design, paper will usually folded along straight edges without stretching, tearing, or cutting. However, a flat sheet of material can also be folded along curved creases, as shown here. The folded surface can be isometric mapping onto a 2D domain. The most influential early work on the design of curved crease surfaces was done by David Hoffman. He discovered the geometry properties of curve folding and also created some examples of curve folding models as shown here. And using the basic theoretic insight, Eric Damain and June Mitania create artwork for the design of origami with curve creases. And Professor June Mitania even had a book called A Curve Folding Origami Design. So there are some pretty examples. So for research, Killian and his colleague developed quad mesh for the reconstruction of general curve crease surfaces. So the recent work of Rabinovich used the discrete net of orthogonal geodesic to modeling developer surface and also the curve folds. So here is example of curve crease origami for the face shield design. So in our project, our contribution is a designing method for curve pleated structure. So we require the structure to approximate given reference shape. We also introduce the concept of principal pleated structure, and the discrete principal pleated structure could be used as a flexible mechanism. So we modeled our curve pleated structure by special PQ mesh. So first, PQ mesh or planar quadrilateral mesh have been widely used in freeform architecture. So here is one example. It's a shopping mall in Australia covered by PQ meshes. The PQ mesh with nearly rectangular panels follow the principal curvature lines. So one special case of such kind of mesh is a conical mesh. So a PQ mesh is conic if at each vertex, the faces around this vertex are tangent to a right circular cone. So for conical mesh, the sum of the opposite angle are equal at each vertex. So the geometry property of conical mesh has been explored by previous work. Here we just give a brief recall of the parts which relate to our work. So curve pleated structure consists of smooth developer surfaces, and this surface can be mapping asymmetrically onto the plane. The basic type including plane and the developer surfaces, which had already been introduced before. So it's natural to model the discrete developer surface as strip or planar chords. So obviously, PQ strips can be unfolded onto the plane. And furthermore, the refinement of the PQ mesh by subdivision and keep the chords planar produce a smooth developer surface in the limit. So if we refine a PQ mesh in one direction, this can give us some developer strip models. So on the right-hand side is a developer strip model. So usually if we unfold the developer strip model onto the plane, there are some gaps or overlaps. But one property of the pleated structure is that if we unfold this curve pleated structure, there are no gaps or folds. Okay, the most important geometry property of a curve fold is that the osculating plane here shown in red, the osculating plane of the crease curve bisects the tangent plane on either side. So these two orange plane are the tangent plane on either side. They have the same angle with the osculating plane. So a special case of curve pleated structure are the principal pleated structure. So the principal pleated structure has constant folding angles around each curve, each crease. So they can isometrically deform onto a 2D plane. During the deformation, the property of constant folding angle is always true. So we call such kind of structure as principal pleated structure. So in the discrete case, a discrete pleated structure is modeled as a PQ mesh. So this PQ mesh should be asymmetric to a planar quad mesh. This means that the sum of the angles for the mesh at each vertex should be 2 pi. So this is the developability constraint. And discrete principal Pleated structure are special conical mesh. So because of the developability constraint and also is the constraint of conical mesh, we will get a conclusion that the sum of the opposite angles equal to pi. Okay, so the other constraint of the discrete principal Pleated structure, the property of is that they always have constant folding angles, and also its offset is always a discrete Pleated structure. So these are some examples of principal Pleated structure. So okay, this is a wood. This wood structure is rendered based on a principal Pleated structure, so which can be folded from a 2D structure. So if we look at the details, we can find out the structure has a constant thickness, so which is an important property of conical mesh. So the property of principal Pleated structure also implies that it is a flexible mechanism. So this is a real model for a principal Pleated structure. So this physical model can be folded continuously from its 2D form. So during the deformation, the constant folding angle is always 2. Okay, so to design and compute a Pleated structure, we introduce the concept of pseudogeodesic. So here, the blue line is a pseudogeodesic. So a pseudogeodesic is a surface curve whose osculating plane form a constant angle with the tangent plane. So here the constant angle is theta. So here this is example of pseudogeodesic with constant angle theta equals pi over 6. There are two special cases. One is that when the theta equals 0, then the pseudogeodesic curve is asymptotic curve. But when theta equals pi over 2, then the pseudogeodesic curve is geodesic. So usually a pseudogeodesic has a constant angle in between. The whole computation pipeline including two major parts. One is the initialization based on the pseudogeodesics, and another is the optimization part. So here we show the initialization. So we initialize Pleated structure based on pseudogeodesics. So here this red circles actually represent some curves, some pseudogeodesic curves. So they are sampled approximately equal distance. And here the red line is the osculating plane of those pseudogeodesics. And then we can offset the pseudogeodesic around the normal direction of their osculating plane alternatively up and down, and we get an initial surface of Pleated structure here shown in orange color. And we assume that after the offset, the osculating plane of the offset curve is approximately similar as the osculating plane of the original curve. Then we will get a conclusion that this osculating plane bisects the two tangent plane in between. So this kind of initialization is good because it satisfies the geometric property of curve folds. So here is a case for the theta equals pi/6. So the initialization based on pseudogeodesics can be applied in two different ways. One is giving a space curve. We generate the surface through evolution. So another way is giving a reference surface. We sample some geodesics on the surface. So here I show the first way. So here is a given curve. We can compute its normal direction, its binormal direction, and its evolutionary direction. So here theta is the constant angle for pseudogeodesics. So here we show two different examples. One is that theta equals 0, and another one is theta equals pi/6. And then we can generate the curves again to build up a surface, and those curves are the pseudogeodesic curve of the evolutionary surface. And then we can generate the initialization of the oscillating of the curve pleated structure as we discussed before. And this kind of initialization is a good initialization. So for a given reference surface, we can prescribe a guiding curve, and then we can sample some vertices on this curve and trace the pseudogeodesics. And then we connect this pseudogeodesics with a quad mesh, and similarly we generate the curve pleated structure. And to emphasize the importance of initialization, here I show example of a bad initialization. So this initialization is generated based on a given quad mesh. So after that, we're using this kind of initialization for our computation. If we require the mesh, this given mesh, to be asymmetric to a 2D plane, then the structure, this is the result. Then the structure will go far away from the reference shape. But if we add the weight of the closeness, then we can never get a planar quad. So here the red means the quads are not planar. So under such of initialization, we cannot get a very good computational results. So in the optimization, we formulate the constraint as energy term. The planarity is represented by the orthogonality of the face normal and its corresponding edges. And the developability is guaranteed by forcing each face of the 3D quad mesh and its 2D counterpart has the same lengths and also same length of edge and also the diagonals. So we also require the vertices to be close to the initial creases, and we also add some fairness term for the curve for the vertices around the curve creases. So for principal pleated structure, we add an additional term to ensure that the folding angles around each crease is constant. So for the objective optimization, we combine those energy terms, and it can be solved by a Gauss-Newton or LM methods. So here we show an optimized curve pleated structure around a nodal curve, and on the right-hand side is physical model. And these two examples show the results of non-uniform evolution. So here it means that for generating an initial curve pleated structure during the evolution, the moving speed of the vertices on the pseudogeodesics are non-uniform. So here is why we can find some parts is narrow and some part of the structure is wider. Okay, so we also use curve pleated structure to approximate this minimal surface, and this is 2D unfolding and is a physical model. So here we approximate a given reference surface with different prescription of the guiding curve, and then we have different design of curve pleated structure. Okay. The second work is freeform quad-based Carigami. So I will shortly introduce this part. So as I mentioned before, Carigami is a variation of origami. So cutting and folding are both allowed. And pop-up design as a famous example of Carigami. So here are two more such kind of pop-up design. So for the research on pop-up structure, Professor Shi Minghu and his team had a publication of SIGGRAPH 2010 on it. So in our project, we'll focus on another type of Carigami. So these are two examples of foldable boxes. And here is its motion from an open state to a closed box state. And here is Pura's work on the design of such kind of box-like Carigami structure, but they can only handle the regular case. This means that the 2D pattern are regular and the 3D boxes are also regular. They can only use such kind of structure to approximate planes. So then what we want to do is to extend the approximation to freeform surface. So here's one example. The closed box is used to approximate a given 3D freeform surface, and the structure can be flattened onto a 2D plane with holes. And there are three types of box structure we worked on in this project. So this is one, we call it box Carigami, or type B for short. So for each face of the reference quad mesh, there is a box structure. The second one we call it checkerboard box Carigami, or type CB for short. So here we can see the difference. The boxes are distributed alternative like a checkerboard. So only one half of the face have boxes and another half are covered with planar faces. And this one, we call it checkerboard Carigami, or type C for short. The only difference with the previous one is that the neighboring boxes are required to share the same edge. So if we compare these three types, we can find out they have different holes when flattened on the plane. So type B has 8-sided holes, and there are 4 pairs of equal edge lengths. And type CB has 4-sided kite shape with 2 pairs of equal edge lengths. And type C has the strongest constraint. Their holes on the 2D plane are rhombus, whose edge has the same length. So the goal of our algorithm is for a given reference surface. We generate a box-like structure to cover its face, and the box shape can be flattened onto the 2D plane, such that the structure can be constructed by cutting and folding a flat sheet of material. So the essential part of this project is a discrete expanding mapping. So this mapping is not a traditional one, such as conformal or asymmetrical mapping. So as shown in this figure, we call the mesh connected by these red dots as a base mesh. So here, the base mesh in 3D is BM, and the base mesh in 2D is BM bar. So mapping from BM to BM bar is kind of expansion. And this mapping requires the principal distortion always be greater than 1. So for a given 3D shape, we map it onto 2D with proper distortion control. And after the distortion has been computed, we can then design the height and the inclining angle of the boxes. Okay, this is the basic idea. And this design then can be used as initial input for further global optimization with the constraint of the asymmetry. So in the global optimization, the corresponding phase in 3D and 2D are required to be identical, and this constraint has already been introduced in the previous project. So here I show some results. So for complex shapes, we have to cut it for mapping. For example, for this Leaning Tower model, we map it with 4 cars. And for this model, we have to cut it into 2 pieces with discrete topology and approximate the whole shape with 2 pieces of flat materials. So to validate our algorithm and design, we also show here some real paper models. And this one is built with another material. So one side is wood and another side is a feather-like material. This is a 3x3 model. Although simple, if we consider this 3x3 model as a basic element, actually this element can be repeated and rotate 90 degrees and connect with each other to form a bigger structure, which could be used as a roof design. So another work I think is quite interesting is the curved Carigami. So similar as curved origami, the cutting lines are not straight. So as far as I know, there is almost no such kind of design before. So what we did is using the idea of subdivision. So we have the design of box Carigami. Then we can subdivide the 2D pattern and also the 3D shape. And then we apply, and the subdivision could be a very good initialization. And then the further optimization with isometry constraint could help us find the curved Carigami design with very high accuracy. So here is the real model for a curved Carigami design. Okay, so the third project I call it shape morphing mechanical metamaterial. I consider this work also as a Carigami related work. So a typical feature of metamaterial is their orthotic behavior. So as shown here, this is an example of orthotic structure. It's a physical model we made with a planar sheet of material. So the model has 2 states, closed state in 2D and open state in 3D. So one goal of our work is to design the cutting lines in 2D such that the open state can approximate certain given reference shape. So an inverse problem is that the open state is in 2D and the closed state is in 3D. So here is also a physical model we built for such a purpose. So more general goal is that the open state and the closed state are both in 3D. So there are some previous work on orthotic structure, such as this one by Professor Mark Foley and his team. They used a triangle mesh for the orthotic design, and they compute an initialization using conformal mapping. And this is another work used quad mesh as its basic designing elements, which published in Natural Material. So here is a 2D design in which the closed state is a square and its open state is a circle. And these are the results used to approximate 3D shapes. But if you look at the fairness of this result, they are not good. So for the design of quad-based metamaterial, we propose a new mapping called constant mean stretching. So here I will use a simple example to explain this concept. So this is a basic 2 by 2 regular quads in a closed state. So the red dots are the barycenters of those quads, and the lengths and widths of every quad are A and B, and the quads connected by the barycenter have the same length and width. So when the structure opened extremely, we can do the same thing by connecting the barycenters. So the quad connected by the barycenter is a square with edge length W. So it's not difficult to find the relation between A, B, and W. So here is the relations. So we define the stretch on the horizontal direction as a ratio of A and W, and define the stretch on the vertical direction as B and W. So here lambda 1 and lambda 2 are the two stretches. Then we will get the conclusion that the sum of these two stretch, or the mean value of these two stretch, is constant value. So this is a constraint we used in the design of structure deformation from a closed to an open state. It's quite simple. So here is an example. The left one is the reference of the closed state, and the right one is the reference surface for the open state. So in the middle, there are two grays. They satisfy the constraints of constant mean stretching. Okay, so first we map these two grays to the reference surface, and then we further optimize the mapped quad mesh. So we use the control mesh. So here the red one are the control mesh. We use the control mesh as our computational mesh to control to implement the constant mean stretching. And when we got the good control mesh, we can derive the original quad mesh and then apply the global optimization of isometry. So the final result is shown on the top. Here are some more results. So here in this example, the closed shape is in 2D and is opened in 3D. Similar, this is the same. In this example, the closed state is in 3D and opened on a 2D plane. This is another such kind of examples. So we can also, so this example is that closed state and open state are both in 3D, but with different reference surfaces. So here we use such kind of structure to approximate a complex shape, such as a leaning tower. So the closed state is in 2D. So for such kind of reference surface, we can also get the results such that the closed state is in 3D. So here we show more examples of the orthotic structure based on some spherical meshes. So here we show different closed mesh, and then we got different expanded orthotic structure. Okay. So another part of this project is the bistable structure. Here's a video to show this concept. So the structure has two stable states, opened and closed. The previous work can only handle the case of regular patterns, such as shown here. Okay, so here's a figure show the basic element of our bistable orthotics. So the left one is the closed state, and the right one is open state. So if we look at the two different colors, the yellow one has a rotation, and the blue one has only translation. So here we show the relation between the two stretches and in the internal design of the rectangles in the middle, such as their width, length, and angles. So in the initialization of bistable orthotics, we use the relation of those geometric properties that I will not explain the details here. So in our project, we extend the previous work or regular design of general designs. So here are some 2D examples. And this is the open state, the bistable orthotic structure. And this is their physical model. And also we have some other results, the closed state, open state, closed state, and open state. We also tried to design 3D bistable structure. So in the design of 3D bistable, the direction of the rotation axis between these basic elements are very important. So here we show two examples. If we look at the 2D patterns, they are quite similar, but the difference is their rotation axis on the thickness direction. So for this example, we also build the physical model. Here you can find the animation, and those two, the open states of these two structures are used to approximate a positive surface on the left and a negative curvature surface on the right-hand side. And these are the photos of the physics model. Okay, so for the future work, we would like to explore more ways design patterns or pseudogeodesics for initialization of curve pleated structure. Our current way is prescribe the guiding curve randomly, but I think there are some better ways to do this. So we are also interested in the reconstruction with curve folded structure that's not pleated structure. So we also would like to investigate multi-stable orthotic structures. And thank you very much for your attention. Thank you.
Hey, thank you very much for the nice talk and covering different aspects of your work about these geometry design. Any questions from the audience? Okay, I have a quick question. Talking about some of these cases like principal pleated structure design, it looks to me that you can formulate these as like soft constraints in the editor terms. Are these sort of how accurate are these satisfied in the final design? It looks like they are fine, but are there any errors that could cause any problems?
Yes, you're right. For these optimizations, actually because there are some of the terms you can never the energy can never go down to zero, such as the fairness term. So I mean the total energy will never go to zero, but is reasonably well, because we have some ways to measure such as, for example, such as the planarity of the phase. For example, if in the engineering, in the real construction of a structure, if the average length of a quad is one meter, and then we can measure the distance between the diagonals. If the distance between two diagonals is smaller than certain threshold, then we consider it as planar phase. So I mean, it's not zero, but it's reasonable well.
Okay, thank you. Yeah, and other side of it, so you obviously you can design between different init reference surfaces. Any restrictions about what kind of reference surfaces can be done, or can they be very complicated, or can they need to be we need to satisfy certain constraints?
I think this is quite a difficult problem. I mean, for manufacturing, I think the purpose is quite different, because if we look at the Leaning Tower, we say such kind of example is complex for architecture, but in the field of animation or other field of computer graphics, this shape is not that complex, right? So
yeah,
I mean,
so it's all depending on the applications, right? So if you want to use a tool as a effective way for architecture design, these are genuinely difficult structures.
Yes, especially if you want to use a single paper or planar sheet of material to approximate some shape, there are definitely some limitation. But I think is a very good question, that what kind of shape can be approximate. But I think is actually a very difficult one.
Yeah, but I think we need to put these into context, right? So if you're intending applications,
yes.
Is that kind of architecture, or these sort of aspects, the shapes are generally difficult to achieve, especially using traditional methods.
Yes.
Yeah. Okay. Any last minute questions from the audience? Okay. Yeah. If you don't have more questions, I think I would like to thank all the speakers and thank all the audience for joining the session today. I hope you all enjoyed this webinar. Okay. Thank you.
Thank you.
Okay. Bye.
Bye.